So, in last class I have discussed about the single slit diffraction. Now, I will discuss the double slit diffraction. So, it is a similar treatment, double slit diffraction. So, now this single slit is replaced by a double slit. So, this is the slit with one slit and this is the another slit. So, both are having the same width A, okay, and there is an opaque space between these two slits, that is length is B. So, here slit width is A, opaque space width is B, and slit separation. So, slit separation equal middle of this slit to the middle of the another slit. So, that is D. So, that is called slit separation. So, here separately I have shown these two slit of width A and their opaque width is B and their slit separation is D. Okay. Now, same way these plane waves are coming, parallel rays are coming falling on this double slit, and then there will be diffractive rays from both slit. Okay. Now, they will interfere. So, these are the secondary wavelets coming from these both slit, and there will be the interference among these secondary wavelets, and we want to find out the intensity distribution on the screen placed here. Okay. So, same wave from the middle of this slit, if I draw a normal and the screen placed normal on this line, and if you consider a set of parallel rays, so this angle is theta. So, same. So, here this whatever this light are coming, so that is E 0 e to the power I omega t minus k x. So, that is here minus k r minus k y sin theta d y. So, if you choose the same way in single slit, we have chosen a point along the, say, if it is y axis. So, it is a y point to y, and there we have considered very small width. So, that is dy. So, your amplitude will be E 0 dy, and this your e to the power I omega t minus k x. So, in that k x, that x basically r plus additional path. So, that is del. So, that del is basically k y sin theta. Okay. Now, here you see here basically what we are doing. So, this is one ray. So, so this ray and this ray. Okay. So, what is the path difference between these two rays? So, if you draw a normal here, so this path are same. So, additional path here. So, that is the basically these are from single slit. So, it will be A sin theta. Okay. So, A sin theta. So, that is the we have written in general y sin theta, and integration we are doing for this part minus a by 2 to plus a by 2 for this part for slit. Okay. Now, for this slit, so basically we can integrate. So, that d, so for this slit width, so d is basically this what we will get d slit separation. So, this b plus half a by 2 plus half a by 2. Okay. plus half a by 2 plus half a by 2. Okay. So, if you, so D is common, D is, so from this part there is no contribution except it is introducing the phased, introducing the path difference, otherwise no light are coming from this. So, that is why here, so from this, so D plus up means this end and minus up means this end. Okay. So, this limit is basically is for this other slit. Okay. So, so from this slit, this part plus from other slit with respect to this, you see this, actually we have to get the, so from this place, this ray, what will be the path difference? So, that will be d sin theta. So, that will be d sin theta, and for this part it will be a sin theta. Okay. So, if you consider that from here whatever, so you are getting the path difference, additional path for this one. So, path is increasing. So, for this one d sin theta, and for this one you are getting additional path. So, a sin theta, basically a sin theta plus d sin theta one can write. Okay. So, this we have made for this part, this integration for minus a by 2 to plus a by 2, and for this one, for this part we are putting this integration limit d minus a by 2 to d plus a by 2. Okay. And so these are coming from the contribution from the two slit, and we will get at P this resultant one amplitude EP. So, if you proceed, if you just proceed same way as we have done, so this obviously this part is same as the single slit part. So, this will give sin beta by beta, A is 0 sin beta by beta. Okay, this part, and this other part it will have also the same sin beta by beta, because plus a by 2 minus a by 2 is there, and in both limit d is there. So, that d is common part. So, it will be here. Okay. So, this part into this part will be for second term. So, basically if you take this part will be common. So, 1 plus this e to the power I omega t minus k r. So, this part will give basically cos gamma e to the power I k d sin theta by 2. So, what is gamma? So, gamma is basically pi d sin theta by 2, and beta obviously pi a sin theta by 2. Okay. So, that's the thing, this path difference d sin theta. So, that is why it is a k d sin theta divided by 2. So, 2 pi by lambda. What is lambda? K is let me just check whether any lambda is missing. K d sin theta. What beta I have written? Beta should contain, is the e to the power. So, I am getting cos gamma. Okay, additional term is additional path. So, that is k d. So, I think on lambda will be there a d a sin theta, k a sin theta, k is 2 pi by lambda, 2 pi by lambda, but where that lambda has gone? I think beta, yes, of course. So, it is not 2, it is basically it has to be lambda, it has to be lambda, because these 2 pi. So, this 2 will go. So, pi will be there and by lambda will be there. So, this not 2, this is a lambda. So, pi a sin theta by lambda, pi d sin theta by there is a gamma. So, ultimately we are getting this term 2a is 0, 2a is 0. Here you can notice for double slit, for single slit it was a is 0, for double slit it is 2 a is 0. So, basically E 0 is we are telling that it is the amplitude per unit length. So, this is the strength of the amplitude of the wavelets. So, per unit length. So, if it is E 0, so opening is A plus A. So, 2A. So, that is why this 2A is 0, that is the amplitude, and this now in amplitude after that is modified with these two terms sin beta by beta and cos gamma. So, your intensity will be EP star equal to I 0 sin square beta by beta square cos square gamma. So, this sin square beta by beta square is obviously for the is the single slit effect, diffraction effect, and this cos square gamma, you remember that for interference. So, this is the term for interference. Okay. So, we are getting basically two terms, one is for diffraction, another for interference. Diffraction for overall this is a diffraction, but one term is basically contribution from contribution of single slit diffraction, and another term is the interference between the wavelets coming from the two slits. So, if I plot this I equal to I 0 sin square beta by beta square cos square gamma. So, sin square beta by beta square you have seen. So, this is the principal maxima, diffraction principal maxima, and then diffraction minima, say then secondary maxima. So, there are more. Okay. And this term cos square gamma, so as a function of gamma. So, both are as a function of theta. So, here that is why I have written the function of theta. So, if you plot, so you will get this type of cos square gamma. Okay. Cos square gamma. So, this is the cos square. So, this graph is for cos square gamma and this graph is sin square beta by beta. So, these two will overlap, and what you will get? You will get this the resultant diffraction pattern from the double slit. Okay. So, as if these are the interference maxima, minima, maxima, minima. So, so difference this in double slit diffraction we are getting interference, but this interference now its intensity is not constant for all, it is drastically modulated with the single slit diffraction effect. Okay. So, you will get this type of variation. So, here at theta equal to 0 you will get maximum intensity, then intensity decreasing. So, now here one thing is that this so it is varying this maxima minima. So, it may happen that there is supposed to be a maxima interference maxima here at the same place of diffraction minima. So, in that case that diffraction interference maxima will not be able to see, because there is no light in that direction, in that particular theta direction. That is why you are getting diffraction minima. So, that we tell this that order is missing. So, that interference order is missing. So, I will discuss that one. So, for diffraction already we have discussed this, what is the condition for diffraction minima, A sin theta equal to m lambda, and for diffraction interference maxima, so gamma equal to n pi. Okay. So, this is the gamma equal to n pi. So, this is the cos term. So, whatever this it was sine term m pi whatever for sine it will give minima. So, that n pi or m pi for cos term it will give maxima. So, this is the condition gamma equal to n pi, that is the condition for the interference maxima. So, for interference maxima d sin theta equal to n lambda. Okay. So, d sin theta equal to n lambda. So, that is the condition for interference maxima. Obviously, for interference minima that will be d sin theta equal to 2 n plus 1 lambda by 2. Okay. So, here important is diffraction minima a sin theta equal to m lambda and interference maxima d sin theta equal to n lambda. So, that is m lambda, here n lambda. So, position of maxima minima, if we consider, we can get the concept of missing order. So, a sin theta equal to m lambda, condition for diffraction minima, d sin theta equal to n lambda, condition for the interference maxima. For same angle, we can write d by a equal to n by m. So, n equal to d by a m. So, n is called basically missing order for mth diffraction minima. So, n will be the missing order of interference maxima. Okay. So, that m and n, that will be decided by this value of d and a. So, interesting feature we can discuss considering d and a value. If d equal to a, so then n equal to m. So, m is 1, 2, 3. So, n is 1, 2, 3. So, that means all interference maxima are missing, first order, second order, third order, right. So, there will not be any interference fringe, interference effect. Okay. So, that is expected, because d equal to b means d is a plus b. So, that means that b will be equal to 0, spacing between the two slit will be 0. So, that way actually it is single slit. So, that is why we will see only single slit effect. Okay. So, when d equal to 2a, so means b equal to a. So, n d by a will be 2. So, n equal to 2m. So, missing order will be second order, fourth order, sixth order. So, they will be the missing order. So, that interference maxima, the position will be exactly at the position of the first diffraction minima, second diffraction minima, third diffraction minima. So, that is why they will be the missing. So, other case, if you d equal to 3a, so then third order, sixth order, ninth order interference maxima will be missing. So, here you can see that this is for second order missing, fourth order missing, means d equal to 2a. So, second order missing. So, this is the central one at theta equal to 0, right. So, this is the central maxima, n equal to 0 basically, then n equal to 1 first order, then second order missing, third order, then fourth order missing, then other side minus n equal to minus 1, minus 2. So, you can see this in center, in principal maxima, diffraction maxima, when we are getting 3 interference maxima, then in lobes, side lobes, we are getting 1 interference maxima, okay, because fourth one will be missing. So, that is why we tell when that order, if three numbers of principal maxima in the central fringe, in the central interference, in the central diffraction maxima. If three interference maximas are there, so then inside there will be 1. Okay. So, there will be 1. So, when p equal to 1, so if in central maxima 2p plus 1 number of interference maxima, then in side lobes p number of interference maxima. Okay. So, when d equal to 3a, so third order is missing, fourth order is missing, sixth order is missing. So, in that case basically in side loops you will get p equal to 2, whereas in central loop you will get this total 5, 2p plus 1 this 5. That means if you find the interference maxima in the central loop, in the center diffraction maxima and in the side secondary maxima. So, how many are there? So, you can basically tell about the missing order, which orders are missing, and from there you can find out basically if you can find out this D and A ratio, D and A ratio. Okay. So, so basically third order will be missing. So, whatever this we are getting this, how many in central, so plus 1 divided by 2, that will be the third order in this case, this 3 plus 1 divided by 2 second order. So, that order second, that order and this multiple of them will be missing, integer multiple of them will be missing, means second, 1 into second, 2 into second means 4, 3 into second 2 means 6. So, that order will be missing, and other case this third order and then 2 into 3 6th order, 3 into 3 9th order will be missing. Okay. So, these are the missing order. Now, if you consider the n slit diffraction, it is the same way you can proceed n slit diffraction. So, that is the grating diffraction. So, here you have n number of slits. So, we have to integrate. So, for single slit E equal to some it E0, instead of E0 I have written C. C is the amplitude of secondary wave source per unit length along y axis. So, as I mentioned, so earlier I wrote E0, so now I have written C. So, for single slit this way we proceed, for double slit this two term we proceed. So, similarly for n slit we will proceed this from the single slit, and then this is for second slit, okay, d plus a by 2 or d minus a by 2. Then for third slit, okay, so that distance 2d and then plus minus a by 2, okay, 2d minus a by 2 plus a by 2, I think it will be plus. Okay. So, for nth slit, so that will be n minus 1. So, this is the third slit, okay. So, 2d, so it is for nth slit n minus 1 d plus a by 2, n minus 1 d minus a by 2. Okay. So, these are introducing basically path difference with this with the light coming from different slits. So, if you proceed, so you will get basically here NAC. So, A 2A for double slit you got 2A. Okay. So, now n number of slit NA, and that E0, instead of E0 I have taken this C. Okay. So, this is basically amplitude you will get, modulated with the sin beta by beta, okay, and another term has come, instead of cos square cos gamma, here sin n gamma by sin gamma, this term has come. Just if you proceed, it is easy to do it. So, you will get this. Okay. So, your I 0 is n square a square c square. Generally n value is for n number of slit, n value is very high, very large. So, that is why I 0 become very large. Now, this is the intensity expression, I equal to I 0 and then this part. So, it is a, so this will give the intensity variation due to single slit, and this will give the for due to interference. So, so if you proceed, so this, so for diffraction that is fine. Now, for interference for n slit, so this term. Okay. So, now if gamma equal to 0 is gamma equal to 0, what is gamma? Pi d sin theta by lambda. So, same. So, gamma equal to 0 or pi or 2 pi or 3 pi n phi. So, then sin gamma will be equal to 0, also sin n gamma will be 0. Okay. So, both term like sin beta by beta, similar situation here. So, so limit gamma tends to n pi. So, this term will give basically plus minus n. So, how it so basically you know sin theta by theta, theta tends to 0 equal to 1. So, this sin n gamma by n gamma divided by sin gamma by gamma. So, I have to multiply 1 n. Okay. So, this limit, if you put limit sin theta by theta, theta tends to 0. So, that way, so both term will be 1. So, you will get plus minus basically 1 or just not 1 n or n. So, so basically condition for pins, whatever we are getting this maximum intensity when we are getting. So, when gamma equal to n pi, when gamma equal to n pi and we are getting for that for this condition. So, gamma equal to n pi means gamma equal to n pi. So, this is giving d sin theta equal to n lambda. Okay. This condition is called the condition for principal maxima. So, is the exact same condition as for interference. We have interference maxima we have seen for double slit. Okay. So, for n slit, so this is not it is not the interference maxima. Here it is maxima, but there are other maxima. So, that is why this we tell this is a principal maxima. This is the condition for principal maxima, and if you proceed, you will get minima. You have maxima, so there will be minima, and then also there are maxima, is this called secondary maxima. So, this is the term. So, n gamma equal to plus minus pi, n gamma equal to plus minus pi plus minus 2 pi, it is the n pi. Okay. If so, then this part will be 0, not the sin square gamma will not be 0, because that case gamma equal to n pi by capital N. Okay. So, this will not be 0. So, that will be the condition for minima. So, here this we have written except 0. So, pi n pi. So, but n it cannot be 0, it cannot be capital N, capital 2, this 2 capital N, etc., because this condition for that case this sin gamma will be 0. So, that is the condition for principal maxima. So, this is the condition for this is the minima, interference minima. Okay. So, this the when it will be 0. So, this is the condition for minima, and that condition d sin theta equal to n. So, if you from here you will get n lambda, d sin theta equal to n lambda. So, that principal maxima. So, divide by capital N. So, that is giving the condition for interference minima, okay, where n equal to plus minus 1 plus minus 2, except this is the 0 capital N to n, that is the condition for principal maxima. Okay. So, and secondary maxima, so in between, so here I have shown these are called the principal maxima, this is the interference. So, interference principal maxima, and you are getting the pi by n, 2 pi by n, capital N. So, these are the up to n minus 1. So, these are the condition, these are the minima, interference minima. So, in between there must be maxima, and that is called that there must be maxima, and that is called the secondary maxima. And condition for secondary maxima is the secondary maxima is d sin theta equal to 2n plus 1 by 2 capital N lambda, because you will get this part n. So, this when you will get this one, when you will get the n gamma will be when pi by 2, 3 pi by 2, but pi by 2 is not allowed, pi by 2 is not allowed. So, why not allowed? If yes, but it start from 3 plus minus 3 pi by 2, 5 pi by 2. Why it is not allowed, that I can say, because the here I here pi by, so n equal to, okay, 2n plus 1. So, basically n is 0 is not allowed, okay, n equal to 0, that is not allowed. For no cases it's the 0 is allowed, because n equal to 0 and n equal to n. So, that are not allowed, n equal to n, 2n is that are not allowed, there are principal maxima. Okay. So, that is why for this case n equal to 1 plus minus 1. So, it start from 3, 5, 7 etc. So, these are the condition from, if you put this condition, putting gamma value, you will get condition d sin theta equal to 2n plus 1 by 2n lambda. So, secondary, these are condition of secondary maxima, and you can check that when you will get between these two principal maxima, if there are n minus 1 minima, so then secondary maxima will be n minus 2. Okay. Secondary maxima will be n minus 2. So, for n slit diffraction or getting, so you will get this principal maxima, and in between you will get minima, you will get minima maxima. So, these are the secondary maxima, and these whole things are modulated with this single slit diffraction effect. So, basically if slit, this number of slit per centimeter or per inch, if it is generally it is very high, if it is around 1000, you know, this I have done for n equal to 6. So, if it is 1000, so now imagine, so within this so many principal maxima you will get, and this most of the intensity will be occupied this principal maxima, and this in between this secondary maxima, we comparatively intense compared to this intensity of principal maxima, these are so weak, and if slit number are higher, so this will be even weaker. So, we will not be able to see, generally we see this type of, and so is similar to the double slit experiment, the pattern we have seen for double slit, similar pattern we will see, only difference is that Here these are the principal maxima. There interference maximum minimum was there. Here we are getting principal maxima, and in between there are many maxima and minima. So, that we may not be able to see. So, and this so missing order in this case, the missing of the principal maxima, and condition for principal maxima. So, the same way for double slit, whatever d by a equal to n lambda. So, you can find out the missing order for the principal maxima, okay, in case of grating. Okay. So, the width of the principal maxima, so this diffraction, this principal maxima is basically pi plus pi by n. So, this is the minima. So, next minima is pi plus 2 pi by n. So, why pi? This we have to see the condition. From that condition you can see. So, this is the principal maxima we get at n equal to pi. If it is pi, so then this one will be pi plus pi by n, 2 pi by n, 3 pi by n. Okay. Similarly, other side minus pi by n, pi minus 2 pi by n. So, basically here gamma equal to this width is 2 pi by n. Okay. So, gamma is this. So, from here sin theta equal to 2 lambda by n d. So, it is the delta theta full width you can get. It is just differentiate it cos theta del theta. So, basically this full width is 2 lambda by n d cos theta. So, half width will be lambda by, half of it will be lambda by n d cos theta. So, half width of the principal maxima is this, right. So, this is required for discussing this other thing. So, now dispersion of the grating, dispersive power of the grating. What is dispersive power? The rate of change of angle with the change of the wavelength. Okay. Diffraction angle, rate of change of the diffraction angle with the change of the wavelength. If wavelength is changed, then what will be the change of the angle of the diffraction for same order. Okay. So, we know this for diffraction principal maxima, that condition d sin theta to n lambda, d cos theta d theta equal to n d lambda. Okay. If there is a change of lambda, so what will be the change of theta, okay, for a particular order n. So, d theta by d lambda equal to n by d cos theta. Okay. So, this is the basically we could tell the dispersive power, dispersion of the grating. So, it depends on the order and it depends on the d value and theta value. Okay. So, and resolving power of the grating is nothing but this. If for a lambda we will get the principal maxima, okay, and for another lambda plus del lambda, we will get another set of principal maxima. Now, this two principal maxima of same order, say first order, for wavelength lambda and wavelength lambda plus del lambda. So, the principal maxima for these two wavelength for a particular order, whether these two peaks coincide with each other or whether these two peaks we can see separately. Okay. If we can see separately, then we can tell this is the resolved. So, two peaks for corresponding two wavelength. So, that means we tell that this wavelength can be resolved. So, that is the whether this grating can resolve it or not. So, it depends on what? So, that is the basically resolving power of the grating. So, Rayleigh criteria for that this is one principal maxima for a particular wavelength and this is red one is for another wavelength. So, now this for same order. So, these two peak if peak of one is at the minimum of the other one and vice versa, for that angular separation we can resolve, we can see these two separately like this green one. Okay. If this separation is less than that, then we cannot see them separately. It will be, it looks one broadened peak, and of course, if it is separation is greater than that, obviously it will be seen easily. So, minimum we need this separation. So, maxima of one principal maxima when it will coincide with the minimum of that one, okay, other one, okay, or vice versa, then it can be resolved. Okay. So, that is called the Rayleigh criteria. Okay. According to this criteria, so d sin theta equal to n lambda. So, for different wavelength, so if we differentiate, so this cos theta del theta equal to n del lambda. Okay. So, del theta, what the minimum separation we need, so that is the Rayleigh criteria. So, this basically this is nothing but the half width of the principal maxima. So, half width of the principal maxima we found that lambda by capital N d cos theta. So, if I put lambda by capital N d cos theta, okay, equal to n del lambda. So, from here you are getting basically lambda by del lambda equal to n small n into capital N, okay, small n into capital N you are getting. So, this is called chromatic resolving power. This resolving power in terms of wavelength, resolving power also defined in terms of the separation of the two objects, whether we can resolve or not. So, but here in terms of wavelength, so that is why it is called chromatic resolving power. So, that depends on the order of the principal maxima, as well as it depends on the number of lines, number of slits in the grating, okay, capital N. So, that is what about the Fraunhofer diffraction. So, single slit, double slit and gratings I discussed. We will demonstrate the experiment in the laboratory. So, thank you for your attention.